Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be looking at episode 4 of our Discovering STM32 series. Following on from our last episode where we got started working on our serial device. So we got our UART class written as well as our FIFO buffer class, and today we're going to be looking at getting a couple more classes done, which will allow us to test all of that code, make sure that's behaving itself, and actually start getting some information sent back to the computer. In future episodes, we're also going to be looking at getting the code done to be able to get the terminal or console that I mentioned previously all working. And that will allow us to be able to send commands to the Discovery device and get that all working. There has also been a couple of upgrades to the stream setup this time around. So if we jump over to our Discovery device, we've got a much better quality camera on that one. And from the testing so far, it actually looks like we're not going to have any issues with that freezing up. But I guess we're going to see that as the stream goes on. So as I mentioned, going to continue on from last time. So if we jump to that one, still getting used to this whole streaming thing. So looking at our code from last time, we've got the UART class that we created, and we've also got our FIFO class that we created. So these are kind of pieces of the puzzle to create our overall serial system. Definitely could be done in ways that are a lot simpler. However, this particular approach I'm a bit of a fan of because it does allow us a bit of additional flexibility moving forward as well. What we're going to be looking at doing today is creating two classes. One which will be inheriting from another. If you've not messed with classes too much, I will be looking at doing a bit of a stream or a video going into classes a little bit deeper. But I will try and explain sort of what's going on and how it all works and stuff as we go today too. So we're going to be creating one class that is basically a base serial class. So a class that is like a black box that is just used to be able to manage a serial in and out stream. It doesn't really care where that stream is coming from. So it could be a file, it could be a UART, it could be serial being sent over Bluetooth. And then we're going to use that base class and inherit from that in order to create a class specifically for UART. Now, the reason why we're going to look at doing that is because it's going to allow us as we move forward to actually create multiple different types of serial device and to be able to talk to them as if there was no difference between them, using the base class. So whatever's talking to those serial devices doesn't know whether it's a file or a UART or serial traveling over some other protocol. All it's going to know is it's talking to a serial class, and that's going to allow us a bit more flexibility once we get file systems and all that sort of stuff up and running moving forward. So I'll try and keep it as simple as possible. If there is any questions come up, feel free to either ask them during the stream or leave them on YouTube. There is also the details which would have been up at the start of the stream. So you can jump on our subreddit or send an email and I'll do my best to get any questions answered there as well. So first things first, get stuck into it. We're going to create another folder here, and we're going to call this QA Systems. So this is going to be storing the various different sort of systems or subsystems we're going to be creating for our OS as we move forward. One of those being the serial system. And inside this folder, we're also going to create another folder, and we're going to call that QSA Serial. So QA for Quartz Arc, which is our project name, the S for system, and add that one in there. Now, of course, we are also going to have to jump in and add these ones to our includes and source location paths. So add that one in there. And I'm going to add just QA Systems on its own, as well as QA Systems, QSA Serial. And we'll add that for our release config as well. So that's our includes done, and also going to add this to that one like so. Now we haven't actually added tools to that one either from last time. A bit of an oversight. Let's get that one popped in there as well. And just make sure we've put in... Okay, I obviously wasn't paying attention last time. So we haven't added that in there either, so we'll get that done too, because we're going to be needing that for our FIFO buffers. So on QA tools, pop that one in there, apply that and close, and let's get some files created. So first things first, we're going to create a header and source file for our serial base class. So this one, let's make sure I did that right. Got something not right in the folder set up there. It's not giving us the options I'm looking for. Where are we? Make sure I haven't made any silly spelling mistakes in here. That all looks correct. QSA Serial. That all looks correct too. Let's give that another try. Still not giving me the header or source file option there. That's a bit weird, but we'll figure out why it's doing that. So this one we are going to call QSA Serial dev for device, because this will be one of the device classes, underscore base, because this will be our base class. And definitely something weird going on with those folders, but we're going to come back to that. CPP. So notice the icons for these files look a bit weird compared to if we jump in, say, this one. And that's typically indicative that we are having an issue with the folders not being set up correctly. Along with the fact that it wasn't giving us the option to just go in and create a header or source file like we get with this folder. So let's jump back into our properties and see where we have a mistake. QA underscore systems is correct. QA underscore systems / QAS underscore serial looks correct. Aha. All right, so we added it for retail and not for debug. Much better. All right. It can be a bit annoying with the cube IDE, where you can get away with modifying both configurations for your includes. For some reason, it doesn't allow you to do it with the source location. So you might come across that. You can do them individually, but have to make sure you don't kind of make the same mistake I just did and add them for one configuration and not the other. So it'd be nice if that worked a little bit better, but that's okay. We can work with that. Now I'm just going to copy and paste our file header from this one. This one will be Systems Serial. This is our serial device base class. And QSA Serial dev base.hpp. And don't even know what date it is today. The 28th. Wonderful. Fix our recursive inclusion up. Alright, and pop this one down here as well. Wonderful. And of course going to be including our setup.hpp there, which then includes our HAL files and the other stuff that we need for our device. So just going to get our CPP file header in there as well. Get that ready to go. And there we go. All right, so let's get our class created first up. Now, there is a couple of things that we're going to want in here. We might look at including our QAT FIFO .hpp, because we're going to actually be using those FIFO classes, 2 of them, in the base serial device as the transmit and receive buffer. And we are also going to need to include memory in here because we are going to be using some unique pointers to hold those FIFOs as well. So we're going to be calling this class QSA Serial dev base. And much with the previous few streams, the code from this one will also be going up onto GitHub as well. So that'll be all available to everyone once this stream is done. And we're going to create a couple of enums in here. Much as I've mentioned previously, if there is any sort of questions or anything like that about particular approach that we're taking, as far as classes or enums or any other bits and pieces that you see being used during these streams or videos, definitely leave a comment and I'll see what I can do to make it make a bit more sense, even if that means creating a video specific to that. So we're going to have a peripheral state enum in here. That will be a uint8t, and we're just going to go perif inactive will be equal to 0, and perif active will automatically be equal to 1. Also going to go with creating a data state enum, and this is basically going to help us as far as situations where we need to track whether there's no data or whether there actually is data that we need to be aware of in relation to the FIFOs. I'm going to go with device type, and this one will be used to help us figure out what actual type of device we're dealing with, whether we're going to be dealing with a USART or UART device, if we're going to be doing serial from a file, where the file is providing us with a serial stream, or we can stream back to the file. So in this case, we're going to call this DT UART. We're going to chuck in DT file because we know that's definitely going to be one that we use. We could also do things like serial over Bluetooth, serial over TCP/IP. to be able to get serial over network, things like that as well. So this is kind of just allowing us to prepare a little bit more for the future when things start to get a little bit more complicated with the code that we're working on. So we're going to go with a couple of unique pointers, one for each of the TX and RX FIFOs. So I believe these were just QAT FIFO. No, QAT FIFO buffer. Alright, so I'll chuck that in there. And we'll call this one m_p TX FIFO and MP RX FIFO. So these will be our FIFO buffers. We're going with unique pointers in this situation because they're a little bit safer than standard C-style pointers. And in this situation, we're not going to be sharing those pointers with anything else. They're just going to be accessed by this base class. So in that situation, it's a safe approach. So we're going to go with, let's pop some peripheral states in there. One for each, the TX and RX. And just double check which way I want to go about doing this bit. Okay. So in our setup file, right back in the first stream, we created this enum here to allow us to return either an OK or a particular error message, in this case QA fail. We're also going to be creating one just to sort of, so we've got a global enum to be able to track whether or not a particular system or device or class or whatever is actually initialized or not. And because this is something that's going to be fairly common across the code base, we're going to create it in here, and that way we can use it everywhere. So let's call it QA Init State, and we're just going to go with QA not initialized equals 0 and QA initialized, which will be equal to 1, as we can see there. So, as I mentioned previously, I'm a big fan of using enums simply because it allows the compiler to sort of keep an eye on us in situations where, say, we've got a uint8 or another data type, but we only want a couple of different states in there, and it prevents us from putting values in there that are not relevant to the particular information we're trying to store or track or that sort of thing. So I'm going to chuck in one of those there, and this is going to help us track whether or not the base class has been initialized or not. Now, all of the stuff that we put in the base class will be inherited by the, in this case, the UART serial class that we create as well. So it'll be as if all of the stuff in the base class exists within the serial class or the UART class as well. So that way we can reuse this for the different serial device types, as I mentioned earlier. So we're also going to want that one there. Let's just call this ME Init State. So that'll be tracking whether that's initialized, and then we're also going to put in a device type here, which will be tracking what type of device. Let's call it ME device type. So this stuff will make a little bit more sense when we get on to creating the actual the UART device class as well. So words aren't working properly for me today, but we'll see how we go. Wonderful. So we're going to put in a public section. We'll pop in some constructors and stuff like that. Now, which way do we want to do this? All right. So first things first, as we've done with a couple of the previous classes, we're going to be removing the default constructor so that that one can't be used, because we actually need to supply this class with the particular sizes that we want for the TX and RX FIFO buffers in order for it to be properly created, as that'll be getting done during the constructor. So for this, we're just going to take our default constructor and we're going to delete that. And we're going to put that in there. I'm going to create a new constructor. Which will have our TX FIFO size and our RX FIFO size. And using a UINT 16 for both of those, as if we used a UINT 8, we'd be able to pop in a value between 0 and 255, and there will be situations where we're going to want more than 255 bytes in the FIFO for some situations. So we'll use the UINT 16T, as that will allow us to supply a number in between 0 and 65,535. In here, actually going to do our member initializer list first up. So mptx FIFO, and that will be standard make unique. So this will actually create the unique pointer, and that will be to a QAT FIFO buffer, like so. And then we also need to supply it with the size so that it knows how big to create it. So we're going to do the same thing for our RX FIFO. Like that. And we're also going to want to do our init state. It's always best to do the member initializer list in the same order that we've popped everything in here. So doing our FIFOs first, our init state, peripheral states, and device type in that particular order. Now, we might also just pop in here a device type so that we can actually provide the constructor with what type of device we're setting up as well. That's better. So our init state will be QA not initialized in this case. Now TX state will be perif inactive, same for our RX state. And we're going to pop in our device type into that one. Alright, we don't need to do anything else in that constructor, so that's that bit done. Alright, so going to be creating a few different methods in here, which is going to be sort of our main interface to interact with the serial device class, and this interface will be reused for all of our serial device types. So we're going to need a few different things to allow us to set up and deinitialize our serial devices. We're also going to need to be able to trigger the interrupt handler stuff, which is also going to be inside this base class. We're also going to need the methods to be able to send and receive data or strings or that sort of stuff as well. So we'll start with our initialization methods. So we'll just call this one init, and we're going to put a void pointer in there. Actually, we'll just be declaring these for the moment. This void pointer is not actually going to get used by the base class specifically, but it will allow us to be able to pass initialization information to other classes that are inheriting from this one if they require it. So again, kind of just planning ahead a little bit. We're going to need a method to be able to deinitialize this one. We're going to need a method to be able to deal with our interrupts. So in this case, this is the method that's going to get called by our UART interrupt handler. And again, we're just going to chuck a void pointer in there just in case any of our device classes that inherit from this need data passed to them. We may not end up needing it, and we may end up deleting that, but for the moment, that's what we're going to go with. Now, we might also pop one up here just to be able to retrieve what type of device this is. Like so, and then actually we might pop that with control methods like so. We're going to want to be able to control when our receiver started and stopped, so we'll pop some methods in for that. And then we're going to pop in some transmit methods and some receive methods. So making sure I'm not forgetting anything as I'm going. So this one will take a C-style string and transmit that. We're also going to have one that transmits a C-style string followed by a carriage return, so that we can do that a little bit easier. We're also going to do one that just does a carriage return. Also need to let it know that we're not returning anything from those guys. And then we might also do one that just transmits raw data. Okay, so this one will take a const uint 8t pointer. So basically just a pointer to an array of bytes, and we'll also want to let it know how big that data is. And then we've got some receive methods. We're going to want to be able to determine whether or not there is actually data that has been received that we need to deal with. So we use that one for. And then create one that just gives us a single byte. And then we're going to create one that also allows us to take a whole chunk of bytes in one go. So that way, again, just giving ourselves some options in how we actually want to be dealing with that. Because basically the serial devices are going to be connecting to things like our terminal or our console, as well as other different aspects in the system. So say, for example, we had two different development boards communicating with one another over a UART link. We might be using our own custom protocol within that link to transfer our data and combine any sort of control signals and that sort of stuff that we want in there as well. So we want to make our base class in such a way so it doesn't matter what we're attaching it to, whether it's a console, whether it's a encoder or a decoder for a particular protocol, those sort of things. It's going to give us the options that we need to be able to make that happen fairly easily. Now we're going to pop in a pointer to a UNT8T there. Now, unlike our transmit where we used a constant pointer, we're not using a constant pointer here because this is actually going to be getting modified and filled with data, whereas we're not actually modifying that with TX data, which is why we're passing that as constant. Also means that as a glance, it sort of gives us more of an idea of what we're actually using that for. Alright, so I think that's all we're going to be needing for those. These guys are all going to get defined in our CPP file. So jump in here, pop those guys there, and let's get this all sorted. Okay, so pop that in there. Now, I'm just going to pop this in here so that it knows that all of these methods are members of the QA Serial device base class. Now, if there's any particular things that you'd actually like to see me touch on in future videos, particular peripherals or approaches that you'd like to see, feel free to also make a note of those so that if something that I find interesting, there's a good chance that I will actually go through and either integrate it into this particular series or maybe even do separate video or separate series on it as well. And again, doing our comments the same style that we've kind of been doing in the last few streams, just to keep everything nice and consistent. And again, it's not so much about describing what we're actually doing for each of these methods and things like that, as much as it is about helping to break the code up so that as we're scrolling through it, it's going to make it a bit easier to see what we're actually looking for. It's those ones, and then we got some transmit methods. Paste that one in there instead of retyping it. Like so. And these are our receive methods. So by the end of this stream, we're going to be looking at being able to have data being transmitted back to serial terminal on the computer. Curious as to why it's not seeing that as a comment. But we shall come back to that. That looks all fine there. Aha, it's because we're returning a data state, which is a member of our class. There we go. Let's fix those comments up there. Wonderful. Now, we are also going to be creating some private methods in here, which are what is known as pure virtual functions. So these guys, we're basically just advising that the class that inherits from this class needs to specify these particular pure virtual methods in order to be a valid thing to be inheriting from the base class. So it's kind of defining the things that the inheriting class needs to have in it in order for that all to work properly. And this will make it a little bit more sense once we get started on the actual device class. Be able to see a little bit more about how these two integrate together with the inheritance and things like that. And again, I will be looking at doing maybe one or more videos or streams just looking at classes and inheritance and things like that, so that they could make a little bit more sense to anyone that finds them a bit confusing. If you're looking at getting into sort of some more of an in-depth look at just how C++ and object-oriented programming and things work in general, I'd actually recommend checking out the Twitch channel and YouTube channel, The Cherno. It's probably got some of the best C++ tutorials for beginners that I've come across. And he is also an ex-EA Games employee as well, so he's actually done coding on things like game engines and stuff like that, which I find is really interesting for when you're working with microcontrollers, because much like a game engine, performance matters. And you get to see that, especially as far as classes and things like that, yeah, if they're done the wrong way, they can have a bit of overhead in terms of memory and processing, but there are ways that they can be done where that's not going to be too much of an issue, which is great for games and microcontrollers in general. So most of my previous approach before getting into microcontrollers was messing with games engines, which is why I find doing this sort of stuff quite fun. Now, why is it not? There we go, spelling error. And that one's highlighted properly now. So, as I mentioned, these methods, it's basically just saying in here that anything that inherits from this class needs to implement these methods within it in order for that inheritance to work. Otherwise, we're going to get compiler errors. So that kind of allows the base class to talk to the class that's inheriting from it, even though the base class doesn't know what type of class is inheriting from it. It's quite a handy little trick. Alright, so in our initialization, we are going to firstly check to see if we are actually initialized first up, and if we are, then we're not going to proceed with initializing again. So in that situation, we're just going to return OK, because we are already initialized. At that point, we're going to call our Init method, which is one of our pure virtual functions that we created. So in this case, what will happen is whatever's creating this serial device, or this serial device class, will call the public method init in order to initialize what's going on within this class. And then that allows it to do the bit of stuff that it needs to do for the base class before it then calls this private method, imp_init, in order to do the particular initialization that's required for the inheriting class. So all of the methods that are going to get accessed from, say, our console or whatever, will be these public methods that we're creating. And then within those, they'll access the pure virtual methods of the inheriting class as needed. Hopefully that makes some sort of sense. It does in my head. And if classes seem a bit not sure if you actually want to get into learning them, they can be confusing until you've started to mess with them a little bit. And then at that point, they can be quite a bit easier to deal with once you've actually been hands-on with them, and different things like virtual functions and pure virtual functions, stuff like that will make a bit more sense. It's one of those things where practice is kind of important. Alright, so if we've gotten to this point, everything is okay. So basically, if our inheriting class doesn't initialize properly, then we're going to fail this here. Otherwise, we're going to advise that we are actually initialized and return OK. Now, in here, for our deinitialization, we're just going to call our imp_init. Now, the imp_, basically popping that there because it's something that is implemented by our inheriting class, so the imp for implementation or implemented. So and we've also got to make sure that at that point we set that it's no longer initialized. Now, so I missed something here, maybe. was called Init State, wasn't it? It certainly was. Okay. It's not highlighting things the way I would expect, which means that we've got some sort of error somewhere. Serial dev base, okay, we're including the correct file. Looks good there. However, I'm missing some semicolons here. There we go. Still not highlighting those, but we'll come back to that. Now, this handler method is basically just going to call our imp underscore handler method and pass that void pointer to it. I'll also go through and get these method names in here as well as we go. All right. So this one is just going to return ME. Let's pop this over here. ME device type. Okay. And then so if our RX is already started, then we don't need to start it again. So we're just going to check for that first up. Like so. And because we've created that enum, if this one is active already, it's going to be a 1, which is going to make it true. So if it's true, it's going to return. We're going to call our imp rx start, and then we're going to set our rx state to say that we are actually initialized, and that one is perif active. And this one, I'm just going to go imp rx stop, so we'll call that method, and me rx state will be perif inactive. Okay, and these guys are rx start and rx stop, like so. Now, so I'm going to run down here and do these ones first. So all of the methods that are actually returning a value will get done first, because then we can compile it without getting warnings about that and find out why we're having issues in some of the other methods there. So if our FIFO is empty, then we're going to return that there is no data. Otherwise, we're going to return that we have data. This will just pop a byte off the RX FIFO and return that. So, like so. Part of the reason why classes can be really good to use is because using these FIFOs like this, we don't even need to understand too much about how things are implemented inside those FIFO classes, as long as we know how to interact with them. And I really like that when things start to get a bit more complicated, like as we add quite a bit more code to this. We're only just scratching the surface with where this sort of stuff is going to go as far as the plans I have for this particular code base. So it allows us to only be thinking of on certain classes and certain layers of abstraction at a single time, which generally will allow things to flow a little bit easier because you're not trying to think about things that you don't necessarily need to. So we're going to retrieve how many bytes here are sitting in the FIFO waiting for us, which we're going to put into usize. And then if usize is not 0, actually no, if usize is 0, then we're going to return QA fail to say that we weren't able to receive data. However, if there is data sitting there, we are going to go through and retrieve it and pop it into the pdata pointer that we're passing to this method. So pdata I equals mp rx FIFO pop. And then at that point, we can just return QA OK, because we have successfully popped data in there. And the benefit to usize being passed as a reference is we can almost treat it like it's a local variable inside this method as well. So we're using it inside the method to keep track of the size and check if there's anything there, as well as in our for loop. But at the same time, we're also passing that size back to whatever called this method as well. So kind of two birds with one stone. Makes it nice and easy. It tends to be a bit neater than turning around and passing a pointer to a UINT 16T, which is kind of what it's doing, but it's passing by a reference instead. And again, if the passing by reference thing doesn't make sense, that's something else that we can kind of cover in a bit more detail as well. Okay, let's try compiling that and see where we're at for the moment. It's going to be at least one error in there somewhere. Looks like a few. Something definitely wrong there. 1,077 errors. That's quite a decent effort. QA Serial dev base not declared. Aha. Should have spotted that straight away. So QA Serial dev base should actually be QAS.
There's no one in your contacts named Hugh.
Personal assistant who thinks that she is actually being spoken to. Alright. That might work a little bit better. Let's see how we go with that. Still something weird going on in there. Need to make sure we end that comment. So that should be Okay, don't think I was paying much attention there. That should definitely be TX start, TX stop, RX start, and RX stop. Still a load of errors going on in there. What's going on with our drivers? Okay. So I'm guessing we've created an issue in most likely this CPP file. Which is having a knock-on effect with a bunch of other files. And as typical, it's probably something simple that I've missed and not realized. Right, let's have a run through this header file, just double check. Okay, so they look correct. Unique pointer, QAT FIFO buffer. Have included QAT FIFO, which is correct. Now going with the correct thing from there. It's not something that is jumping out being completely obvious to me at the moment. Could be something that we've done in the FIFO that it's not liking as well, because it's the first time we're actually including it. Let's have a look at okay, so that's passing that correctly to there. This is being passed to the constructor for our FIFO buffer. Okay, that all looks good there. in order to get this many errors, there's got to be something that's got a bit of a knock-on effect to other files. Just for the hell of it, let's try this. Comment out all of those methods there. Let's see what change that gives us. It's got to be something silly. Those guys all look good. It's also showing up in GPIO as well. What's it showing us in here? Multiple types in one declaration. Maybe something we've messed up with our curly braces. Genuinely got me scratching my head a little bit. I like strange bugs. Prefer them when they're not there, but also fun to try and find as well. Alright. That looks good there. You know that class works correctly, so the issue has to be somewhere else. It's a matter of looking at where all the errors are that are actually cropping up and trying to trace that back to where the actual error is. And I missed a semicolon. Definitely not the first time I've done something silly like that. It's one of the reasons why I actually enjoy doing the streams. I don't think it's a bad thing for people to actually get to see some of the silly mistakes that you can make even after you've been doing programming for a bunch of years. Probably doesn't help that I enjoy doing these streams late at night when I'm slightly asleep, but if I wasn't streaming, I'd be sitting here coding anyway, and probably making the same dumb errors because I'm half asleep. Alright. So, hopefully that was entertaining. So, no errors, no warnings. And it's always fun to see what can happen when a semicolon is missing. Alright, so that should all compile correctly as well. Get some coffee happening. Stream looks like it's maybe still behaving. Guess we're going to find out. Alright. So let's get these methods done as well. And then that's basically our base class done. And then we're going to look at getting our UART serial class done. And then we'll get one of them created and set up, get it all working, and test to see if it's going to work. So next stream is possibly going to be looking at using the FMC and getting the 16 megabyte SD RAM on this discovery board up and running, because we'll need that to store frame buffers for our LCD screen. So that way we can actually get the screen displaying something, get a lot of the drivers and stuff up and running first up. So that way, if anyone has one of these boards or even a similar board, a lot of this stuff can be used for the Nucleo and Discovery boards for various different types of devices. They're mostly fairly similar. And as mentioned previously, we will also be taking a bit of a look at some other different boards as well as we move forward. So I do have a F4 Discovery board as well as some H7 and F4 Nucleo boards as well, which we're going to take a look at. Okay, so this is going to be basically identical to this one, with the exception that we're also going to push a carriage return onto that FIFO in here as well. So mptx FIFO push, and 13 is a carriage return in ASCII. So basically iterating through the string that comes in here and pushing each of those bytes or characters, same thing, onto the transmit FIFO in those methods. The other thing that we're going to need to do is come up to, we might do this in the HPP file. I need to include string.h so that we can actually make use of that strlen method there, so that we can actually track or check how long the string is. So this guy here, it's one of the C language library string methods. We will be doing some stuff with C++ strings, some stuff with C style strings. I like to sort of mix it up a little bit. There'll also be just some raw methods to actually just handle arrays of characters as well manually. So a few different approaches I like to take, just depending on the particular situation. So this one is pretty simple because we've just got to send a carriage return. Depending on how your serial terminal and things are set up and how you like to approach things, sometimes you might do a carriage return and a line feed character as well. However, I tend to find it easier if we're just doing a carriage return or ASCII 13. And you'll find in most serial terminal software you can get for various computers, it will allow you to select whether you want a carriage return or a carriage return and a line feed, or if you want something custom, which the particular one that I use also provides that as an option. So, and then for this one, I'm just going to go for UART 16T, I equals 0, I is less than usize I plus plus, mptx FIFO push p data I. So just pushing the data from this pointer into our tx FIFO. And then, as we've done with all four of these tx methods, the tx start is just going to trigger the transmission, assuming that it hasn't already been done. So if we're sending multiple, say, strings one after another, it could be that transmission's already started from the first one and it's still continuing. So inside this method in our inheriting class, we're going to check and see whether or not we actually need to trigger it as well. But we'll see that as we go in and look at that. So just build that, make sure that all looks good. 2 errors. What do we got there? It's in our CPP file. Down to our error here. Now, they should be lowercase. Wonderful. All right. So just going to take a quick bio break and then we will get the next class sorted out, test the whole thing, make sure it works, and that will be good for this stream. I may be going to do another stream later on this evening, see how I go, but about halfway through this one. Excellent. So I shall return in a moment. And we're back. All right, so now that we've got that base class out of the way, let's get our UART class done. So I'm going to want a header file for that one, which we will call QSA Serial dev UART.hpp. Keep forgetting to tell it not to use the templates. QSA Serial dev UART.cpp. Copy our headers over. From that one. Pop that one in there. Might help if we spell properly. And that will be our UART class there. Make sure we fix these guys up. We will keep those guys there for the moment. May not end up needing them, but we'll go with that for the moment. Okay. Kill. Everything there is correct. And get rid of that one. And this one is going to be including our HPP files. So QSA Serial dev UART. And that is CPP. Wonderful. Alright, so in here we are going to create QSA Serial dev UART. Like so. Alright, so actually forgot, this one's going to be inheriting from the other one. So QSA Serial dev base, so that all of the features that we've just put in the base class will be included in this class. It's also going to allow other aspects of the code to be able to access this dev UART class as if it's just the base class, as I mentioned earlier. So in here we're going to include QSA Serial dev base, so it knows where to find that. And we are going to have some private stuff and some public stuff. So also going to need to include in here QA driver UART.hpp, because there's actually going to be one of those in this class. So this one is what's actually going to allow us to have access to the particular UART peripheral that this serial class is going to be accessing. If my brain's working correctly. All right, let's change this up a bit. So we're actually going to make that a unique pointer to our QAD UART. And that will be ME, let's just call it ME UART. Alright, now much like we've done with a lot of our classes so far, we're going to be deleting our default constructor. So that one equals delete, and we'll get rid of that. Now, we're going to create an actual initialization structure, so a data structure to hold the particular initialization data that we need to get this class all set up. So we're going to need the information to be able to set up our UART, and in previous stream we did actually create a data structure to be able to do that, which holds information such as which pins we're using, what UART peripheral we're using, what our baud rate and things like that are as well. So we're going to be popping that in there. And we're also going to need to keep track of which UART peripheral we're actually accessing here, and that'll come in handy when we go to do our interrupt handling and stuff like that. So let's pop that in there. Let's just line these guys up. Actually, we'll create that structure first. Let's call it QSA Serial Dev UART Init Struct, and we'll make that a type definition. So QSA Serial Dev UART Init Struct. Inside there, we're going to want a QAD. So this is the structure that we've created to be able to initialize the UART. So we're going to be including one of those. So QAD UART Init Struct. And let's just call that UART. And we're also going to need to supply the size for the TX and RX FIFOs in the base class as well. So we'll make those uint16t, and we'll call that TX FIFO size and RX FIFO size. So let's create a constructor for this that accepts that init struct, like so. And we might go with a reference to that structure as well. The reason why you use references in certain places is to avoid the system from actually making a copy of what you're passing it. So in this case, it's actually passing a reference to the original copy. Certain situations where you mightn't do that, which I will hopefully go over when we get to some of those. Okay, and we're going to want to initialize our base class here, and that's going to need to be supplied with our TX FIFO size, RX FIFO size, and what device type. So pop those in there. So that will be TX FIFO size, RX FIFO size, and the type of device will be QAS. Actually, I don't need to do that because it's inheriting from that, so it'll be able to see it anyway. I'm going to be using this DT_UART to let it know that we are creating a UART device. So that is basically calling the constructor for the base class. So this one here that we created, make sure that anything that's involved in the base class is all initialized, along with any of the stuff that we're going to be initializing specific to this inheriting class. So in this case, we're going to need to do me perif, and that will be part of our UART structure, so that'll be this one here. So that one, and we're also going to need to go MEUART make unique, as we're using a unique pointer, and the type for that one is QAD UART, and we need to pass should realize I'm passing by reference, not an actual pointer, which means rather than referencing it as if it's a pointer, we need to be accessing it as if it's a reference, like so. Excellent. All right. Now that's it for the public-facing stuff for this particular class, because most of that stuff we put in the base class, most of the methods that are going to be accessed from outside the class. However, we do need to implement all of the pure virtual functions that we put into our base class. So these guys here, we actually need to implement them within our inheriting class. Otherwise the compiler is not going to be super happy about it and it's not going to work. So in here we are going to go with, there's a void pointer for that one. There was, I also need to specify that we're overriding these ones. So we're overriding the virtual methods that we put into our base class. So we've also got to do imp dinit. That wasn't being passed anything, and that will be an override. Let's make things a little bit simpler for ourselves, and let's just pop that one over there. That way we can see both at the same time. Alright, so we're going to need a void imp handler. That one also takes a void pointer and is overridden. TX start, TX stop, and that is all of those done there. Okay, we'll pop this guy back there for the moment. Jump back into this one, and we're going to need to do the definitions for these guys in here. Let's move these back across. Let's do a find and replace on this one. So we'll replace our override semicolon with a open curly brace. Like so. And this will be QSA Serial dev UART. It's UART, and that's an initialization method. Let's just grab this guy first. Get these popped in here so that the compiler knows what these methods belong to. Call that not IRQ handler methods. And these guys are control methods. Like so. Put their names in here. And making sure we keep everything nice and consistent with how we've done all of our commenting for all of our other files. And might just pop some comments in here just to help break things up a little bit as well. That one, and for our control methods. Excellent. All right, that's all of that done there. Let's get some code thrown into those guys. Now, let's just cheat a little bit. Go with the good old here's one I prepared earlier. So actually, no, we won't do that just yet. Save that bit for when we actually start to implement our dynamic interrupt system. So basically what that code will be doing that I've just deleted is allowing this class to automatically register itself for the interrupt for the specific UART device that it's going to be using. In this particular situation, we're going to be doing that manually initially, again, just to test that this whole serial thing is actually working the way it needs to. However, in here, we are going to want to make sure that we deinitialize our UART itself here. So calling the methods that we've created in this particular class to get the peripherals set up and free everything again once we're done with it. Now, as far as our actual IRQ handler, first thing that we're going to need to do is retrieve the handle for that one so that we can actually check the flags for the particular UART peripheral. So for that one, we're going to make use of the get handle method that we created in here. That one there that passes a reference to the handle. And then we can use that to check to see what's actually going on in this. So this code here will actually be being called by the interrupt handler itself. So in this case, we're going to have two different interrupt flags that we're going to look at. The first will be our RXNE, or RX register not empty, and our TX register empty, or TXE interrupts. So how UART get flag, pass the handle, that one, and we want to check the RXNE flag. So if that flag is set, then we need to do something about receiving the data. might do it slightly differently than the way I've done it previously. Okay. UART. I believe that was data RX that we called it in there. Let's just double check that. Interesting, it looks like we may not have implemented a couple of the methods that I would have expected, which is correct. So let's create a couple of methods in here. We are going to go with, let's call them data TX and data RX. Like so. So in this instance, we're actually going to be directly accessing the transmit and receive data registers for the UART rather than using the HAL for that. So we're going to need to grab our CPP file. And these ones go in here. Make life a bit easier, we'll just copy and paste that. So no point having the UART class if we've actually got no way to give it data or receive data from it. Copy that, pop that in there. Like so. Data RX and data TX. And in these ones, we're going to need to put data in our TXD or TDR register and retrieve data from our RDR register. If you're using a F4 device, it only uses a single register address for both transmit and receive, in which case I believe it's just called DR. However, in the F7 devices, it does actually have a separate TDR for transmit and an RDR for receive. So two different addresses for those registers. So just be aware of that if you are doing this with a F4 device. We will see that when we have a look at some of those anyway. So our instance is basically just giving us direct access to the registers themselves, which does make it quite easy. This time, however, we're going to return that from the RDR register, and because that register can actually hold more than 8 bits, we're just going to end it with the first 8 bits set to make sure that we're actually don't really need to, because we are returning a uint8. So let's just do it like that. So that'll give us those methods that we need there. Now we can jump in here and actually make use of those. Okay, so pulled the data out of the UART, and that's got to go into our RX FIFO. So if MERX state, so if our receive is enabled, then we are going to put what's in UData into that FIFO. And we also need to make sure that we clear that flag as well. Otherwise it's just going to immediately call the interrupt handler again. That should be clear flag. XNE like so. In this case, we are going to go how UART get flag, and this time we're going to check the TXNE flag. And make sure that we clear that as well. First up, we're going to check if our TX FIFO is empty. So in this case, if that's not empty, then we are going to look at transmitting some data. Let's chuck a curly brace in there, else. In this case, we're going to go with MP UART data TX, and we need to pass it the data from the TX FIFO for that. So we'll go pop like so. That should be MP UART. There we go. Alright, that's highlighting correctly now. And if there is no data being stored in the FIFO ready to be transmitted, then we can actually look at stopping the transmission at this point. So we stop TX, and I'll also set our METX state to let us keep track of the fact that we are no longer transmitting. Like so. That's basically the interrupt handler there, so that will actually get called from the handlers.cpp file that we created in the first stream. And we also need to implement these guys, so TX start, TX stop, RX start, and RX stop. And in that situation, these are all pretty simple because we're just going to access those particular methods within our UART class. So start TX, MP UART, stop TX, start RX, and stop RX, like so. That all looks good there. Looks like the stream is still behaving itself. And just to check while that is compiling, it looks like that camera has dropped out. Six errors. Let's see what's going on with those ones. That should be a P there. And forgotten the particular names for those guys. No, missed a underscore. That one. Spelling error there somewhere. Okay. It should be TXE, not TXNE. There we go. It's TX empty and RX not empty. Still 3 errors. What do we got going on there? Okay. Passing a reference to that, not an actual pointer. Let's just double check that. There we go. Get handle. Just passing a reference to that one. In which case, we need to make sure that we are passing a pointer to that to this method. And these ones. Two errors. That's because I didn't spell it properly before. Alright, definitely not enough copy this evening. However, that is our UART serial device class done. So there has been a fair bit that's gone into actually creating this serial system. Again, there's a lot more simpler ways to do it. Definitely done a lot more simpler ways just using standard C code. However, this is going to give us the flexibility that we need moving forward. It's also, if you're following along, going to be really good practice for getting used to how classes work. So having classes inside other classes, as well as inheritance and things like virtual methods and all that sort of stuff as well. The more you do that sort of stuff, the easier it will become, and it's all stuff that's really worth knowing. All right. So essentially, the last bit of this stream is basically just going to be looking at getting one of those created. So our serial device, our UART serial device, and then giving it a bit of a test, make sure that we can actually send some strings from the discovery device to the laptop, and make sure that that is all working correctly. So to do so, we're going to need a serial dev UART. I want to point to that one, and let's call that serial underscore UART. These guys that are in here are all just going to be temporary anyway. They will be getting replaced as we sort of get more into depth with different stuff. So we're going to want serial dev UART there. All right, and then we're going to have to go out and go through and fill out a initialization structure for that one, and then get it set up and initialized, and then we can look at testing it. I'm going to do that all in here prior to actually getting to the processing loop. And let's just pop that one there so we can reference it. Alright, so we will grab one of these guys. Oops, struct. No, can't spell. And let's call him S Serial Init. Alright, now there's a few different bits and pieces that are going to have to go into this one. So I've already popped in our information that we need for that. It's all being put into defines in our setup.hpp during the last stream. So let's go with, do this stuff first. So our actual UART is going to be UART1. Let's check that I'm spelling that correctly. That is defined in here. So it'll be QAD_UART1. Just to let it know which particular peripheral we're using. We are going to go with our 57,600 baud rate for this one. And we're going to set our IRQ priority, which is this guy down here. And not worrying too much about what the actual priority value is at the moment, because it's going to be the only interrupt that we're using for the moment. Also need to let it know what our TX and RX pins are that we're going to be using here. And our alternate function, TXAF, and same 3 for our receive pin. And the particular UART and pin combination that we're using is actually going to allow us to use the serial via the ST link. So means that we can do that with the same USB connection that we're programming the device with, which is something I find really useful. That should be RX pin. And our alternate function. And if you were just going to use like a single UART set up one way and that's all you were going to do for that project, this is probably kind of overkill. Typically I would just hard code everything using C code in that particular instance, but we are going for that added bit of flexibility with how we're setting things up for this particular project. A lot of that is going to become a lot more clear when we get a bit more in depth. So some of the things that we're going to be doing will allow us to have more flexibility and more easily monitor a lot of what's going on with the system, due to the fact that we're aiming for something that's more along the lines of an operating system rather than typical microcontroller code. So think I mentioned during the first stream, is sort of see how far we can actually push the device before it starts to break. And from my experience with these particular boards, that's pretty far. And have a bit of fun with them. Especially once we start getting the LCD and touchscreen and audio and a bunch of the other stuff all in there as well. As I mentioned previously, we were doing things like using a ESP32 to be able to provide Wi-Fi and things as well. There is also our LAN Ethernet connector on this board as well, so potentially going to be using that too. That all looks good there. Get this guy initialized. So in order to do that, we call him serial_UART. And okay, so serial_UART equals new QAS Serial dev UART and pass it that structure. Right, so much as we've got here. Alright, now that also needs to be initialized. Now let's go if serial_UART init, pass it a null because it doesn't need any additional information at the moment, equals QAOK. So if we know that it's initialized correctly, then we'll try sending something. So serial_UART. Let's go with txstream_cr hello world. So we've gone through the process of actually getting it to blink an LED, which is kind of hello world for microcontrollers anyway, but now we're going to do the good old hello world thing for serial as well. No errors, no warnings. Now, this is the particular serial terminal that I like to use. If I can even remember the name of it off the top of my head. Used a few different ones prior to this. Now this one is not in there. It's called. Cool term. Yeah. So can't even remember the name of the one I used to use previous, but the benefit of this one, and the reason why I use it, is because it's got some cool options for allowing you to actually send files and stuff like that to the device. So in some of the projects I've done previously, I think one of the previous ones I was set up a CPU on an FPGA, built a custom CPU from scratch just for the fun of it, and was actually using the F7 discovery board to basically control certain aspects of the CPU and SoC in that instance, including being able to type up assembly files for that CPU on the laptop, send them over to the F7 discovery, get it to assemble them, and then upload the machine code to the FPGA from there. So that was a bit of a fun project. And some of the stuff that I want to have a bit more of a look at once we actually get into doing a bit more on the FPGA side of things. So we want that one. Definitely builds. Let's pop that on the discovery device. It'd be wonderful if that camera wasn't dropping out, but thankfully the stuff that we need to be able to see is going to come through on the serial terminal anyway. Okay. Now, something there that's not working quite the way it should do. Let's pop those back across there. Ah, okay. I know what I've forgotten. Jump in here and go to our handlers.cpp. You also need to make sure that interrupt is triggering the correct method in here as well. So I'm going to just copy that over to handlers. Just going to extern that. And then if we go down, haven't actually created it yet, have we? No. So we're going to need our handlers.hpp, and that will be void USART1 IRQ handler, I believe. Let's just double check that. If we jump in here, we'll see the list of all of the IRQ handlers. Now looking for, that is correct, so name of that one is USART1 underscore IRQ handler. Like so. Copy that, and this can go in here. Excellent, and that will be calling serial underscore UART. Like so. However, this is also going to want us to include our QAS Serial dev UART.hpp. Excellent, and that all looks good there. That one is in the base class. And yep, okay, so that's all correct there. We're passing it a null because it doesn't need any additional data. Builds okay. Let's see if it runs okay. Alright, not locking up like it did. And we have hello world. And if I hit the reset button on that board, beautiful. Alright, so those last two streams worth of code working absolutely perfectly for us, which is good. So that now gives us the ability to use the serial as a debug device effectively. So we can look at printing stuff out to the serial terminal as needed to help us debug any potential issues that we come into moving forward. Wonderful, and that's nice and rapid as well. Pretty much instant as soon as we hit the reset button, which I like. So that is our serial code for the moment. We will be coming back to this at some stage and actually creating another class that is basically a serial manager, and it will basically allow for the management of multiple different serial devices, whether they're UART devices like the one we've created, whether they're file devices, or other devices such as doing things like serial over Bluetooth or serial over TCP/IP, things like that I mentioned earlier. So it'll basically just be one system that handles all of the serial type stuff, which is why we created our serial device base class in the first place, because that will, as mentioned earlier, allow us to have a whole bunch of different types of serial devices, but be able to access and manipulate them in the same ways using these methods that have been defined in the base class. Like I said, if people are interested, I'm happy to look at giving a bit more information on classes in a future video as well. However, if you're new to classes and object-oriented programming and stuff like that, I would definitely recommend checking out the Cherno's Twitch channel and YouTube channel. Try and remember to pop a link in the description for those guys, because in general, he has some really good C++ tutorials. And although he's dealing more with Windows programming, all of that translates over to what we're doing here as well. And I find out of all of the different people I've watched that produce tutorials, his are really quite easy to follow. So, like I said, I'll try and remember to pop a link in the description for that one. Our next episode on this particular series, we are going to look at getting a driver set up for the FMC, or full speed memory controller, I think it's called, which will then allow us to make use of the SDRAM chip that is on the discovery board. So effectively the STM32 on this board does have 0.5 MB of RAM, as we can see down the bottom here. However, there is also a 16 MB SDRAM chip on the board, which we kind of need that memory to be able to get the frame buffers set up for the LCD panel. Don't really have enough space in the inbuilt RAM to be able to do that. And that's a nice easy one. That should be a relatively short one compared to some of the streams so far. So I hope some people have at least found this a little bit interesting. If you're watching this on Twitch, I would love it if you followed the Twitch channel. If you're watching it on YouTube, definitely would love it if you click like, click subscribe. Would definitely mean a lot. Have a lot of fun doing this, and the whole reason I'm making these videos is so that I can sort of share what I'm passionate about. If I wasn't sitting here streaming this now, I would still be sitting down writing code. So hope it wasn't too boring for people. If you'd like to help us moving forward with some of the more advanced stuff that we're going to be doing, we do also have a Patreon. And it's kind of the approach we're going to be taking with that is a lot of the simple code, like the code from this video, will be freely available to people on GitHub. However, with some of the more advanced stuff that we do as we start to get more in depth, definitely feel free to follow along with the videos. But if you want access to that code, that's going to be available to Patreon members or to patrons. So thank you so much for watching. Again, any questions, the contact details will come up shortly. Jump on our subreddit or send an email, leave a comment, any of those things, and I'll definitely see what I can do to get those answered for you. So hope you all have a wonderful evening or day or night or whatever it is where you are, and thanks for watching.